So this is like recording, and so Gordon can look at it later. All right, so let's go back up, and then we'll start talking about what a arithmetic series is. Okay, let's see, 2 to 1.2 arithmetic series. Okay, so let me start. Okay, so here is the number line. Okay, it's actually, yeah, let's imagine this being the number line. And where I'm not gonna number it, a sequence you can imagine is as, say, a group of students. They're standing in a line. They're equal distance from each other, A1, A2, A3, A4, A5, A6, A7, and A8. Or you can imagine this is like an army, right? Soldiers are standing in formation. They are like standing on a grid, and they're equal distance to each other. This is like A's, like A1, A2, comma, A3, A8. This is called a sequence, right? So this is just basically a line of numbers. They're like individual. You can't do anything, right? But when we do, when we want them to actually do something, we're like putting them in relationship to each other. We're calculating it. That's when the action, the math action actually happens. So when we're thinking about a series, it's actually a sum. You add up these numbers. So when the series say a series of S4, it basically is everything add up to from the first term to the fourth term. So this equals to A1 plus A2 plus A3 plus A4. This is the sum of the first 4 terms of this sequence. Okay, imagine if this is an infinite sequence, it goes into infinity. We're studying the sequence. We can't really, like, we know the relationship when we start the sequence. We know that you just keep going up the same steps into the future, so we can describe that. But how does this help you? We study also the sum of the first n terms, right? If I was to say and like go to the 7, then I go to A1 to the A7th term. So now I have a new way of thinking about this. Is ASN equal to summation of I equals to 1 to n AI. That means the sum of the first n terms. Okay, so that is our definition of the sequence. And the definition is the same for geometric series. It's the first sum of the first n terms of a geometric sequence, right? So the relationship between sequence and series, like between this and that's the same. It's the sum of the first n terms. However, because the relationship is different, the actual property of this is different. Okay, so now we have this. We actually learned this, we touched on this before. So I'm going to go through this chapter relatively fast. I'm not going to go through each individual one. If you remember at the very beginning of the very first chapter of pre-algebra, there is a trick of doing summation of, the first n natural numbers. As suppose we add it to 100. What we're saying is we connect the first, like we do this, we end up with the same number equals to 101 multiplied by 550 times. And yeah, right. So this is like 5050. We learned this like the very first lesson. So now we go back to that. So what we have here is basically, if we want to extrapolate from this trick back then, is to see it as a sequence. So now we have A equals to 1 plus n minus 1, right? A equals to n, an equals to n, the nth term equals to the n, number n, right? So this is the simplest sequence we can have out there. So what we want to extrapolate is to say, can we have a common rules to describe this, right? So what this happens is you add the first term, you add the last term, and you multiply by number of pairs, which is half of the number of terms we have here. So 50 is 100 divided by 2. So what we're saying is, if I were to add first term, a1, plus last term, an, divided by 2, the average, and multiply by number of terms, and that becomes Sn. Okay. So let's see. Right. So we can visualize this. There's another way to think about it. Is we can list two series. We can list the same series twice, one in the ascending order, one in the descending order. So in this case, you can write it from 1 to 100. Write it again from 100 to 1. You're basically just rearranging the term without changing all the terms. So we're adding the first n terms together. Okay, this is the sequence and this is the series. And when we line them up, we end up with twice the series equals to 101 plus 101 100 times. So 2s equals to 101 multiplied by 100. So s therefore is half of that. 101 multiplied by 50 is 50/50. Okay. You can always, this is a trick, you can always duplicate it and then try to find a clever way to arrange it and get to your answers quickly. So this generalized to this formula. Yeah. So okay, this is the general formula for Sn for a geometric term. So we know a1 equals to an equals to a plus n minus 1 multiplied by d, right? So this is expressing it in terms of the member of the sequence. This is describing it in terms of the parameter, you can say, of the sequence, right? So now if we plug it in, we have a plus n minus 1d divided by 2 multiplied by n. Simplify, we have 2a, this equals to a plus n minus 1 over t 2 multiplied by d. Actually, I can't write it this way. Sorry, let me undo it. This is actually, I forgot the n. This is an plus. Okay, so this also multiplied by that. It just looks off to me. So an, the first term, the common term, if you add up the n term, there's n of them. So an is a common term. And the distance, right? When the distance is equals to 1, then you have this formula. So you're basically doing this yeah. Right. So this is the formula for Sm. It is not simplified over here. It's basically the number of terms multiplied by the average of the first and the last term. Right? That's how you describe it. Average of the first and last term. So you try to understand it. And then I can try to apply this to a couple of examples to see, right? So we have a theory, like the first one is this. Okay, -3 plus -1 all the way to 15. So if I were to say the first, evaluate this, what I have is -3 plus 15 and take an average, multiply by number of terms. I think there's 10 of them here, 10 terms. So I end up with 60. Okay, so try to do the second one. Evaluate the following. So I know it's the average of the first term, 73, plus average the last term, 7 divided by 2. and I just need to figure out how many terms there are. And apparently the relationship of this is subtracting 6 for each one. How many terms? So term 1a equals to 73. an equals to 73 minus 6 and minus 1, which equals to 7. Okay, so this means let's see, this is 6 and minus 1 equals to 66. Yeah, 66, and therefore n equals to 12. So 12 multiplied by 12, and this is 480. Okay, so you can apply this. Are we good? Are we following? I feel like I'm going pretty fast. I'm skipping a few steps here.
I can follow. I mean, I learned this before, but
Right, I know you did. What about Kevin or Yo-Yo? Are you doing okay? I feel like it's pretty confusing. It could be pretty confusing for you because I'm skipping two steps. I'm not gonna do the last one because it's fractional. It doesn't really change much. It's still the same logic, the same rules applying. It's just a little bit more mathematically challenging because there's fractions. So what, if anything, you will remember, right? Just remember that we did learn this trick at the very first lesson of this whole course 2 years ago. Right now, we actually bring it together, have a way of describing it mathematically, and it's called a series. So the series for arithmetic, the arithmetic series is this. You know, if you need to remember this. It's the number of terms multiplied by the average of the first and last terms. Okay, you can even tie this to geometric things we learned. So imagine if we have like a trapezoid, right? This is like base 1 and base 2, and this is a height. Okay, you can even imagine this as the first term. This as the last term. And there's like, you can cut this into many different equal layers. Each layer is the same increment from the previous layer. So this becomes your sequence. And if you want to add up, if you want to look at the series, you're basically looking at the sum of all these layers. So that's almost the area of this trapezoid. And that formula is B1 plus B2 divided by 2 multiplied by the height. The height over here, if we cut it into n layers, and then that's n of it. So it's the number of layers we have, and which is the height. So this is how you can relate this to this algebraic concept into a geometric format, or not format, like concept. And actually that is how we will eventually get there when we learn calculus. Okay, so this is all setting up for calculus. You can even treat this as pre-calculus. So I think I'll be done with this part. Maybe just briefly mentioning this formula for the sum of first n positive integers. We have this. So we have, the first term plus the last term divided by 2 multiplied by the number of terms. So we have this formula, which we learned before, right? For how many positive integers n does this evenly divides n 6n? So that's just set it up so you can actually solve it. This is AMC 12, so I'm not going to really get into it. So Anders, if you want, you can actually, I think you probably already did this. The key is to express the sum in terms of 6n and see what numbers qualify. There's only a limited number of n's that qualifies it, and then you figure out the formula, and then you isolate the options for n, right? Find the formula for the sum of first n positive odd numbers. That's just n squared, which we also learned in pre-algebra. And because n odd numbers are, you describe it in terms of the sequence, and you calculate it out, it just so happens to be n squared. Okay, I'm not going to spend time on these today. Just quickly talk through it. The sum of the first 9 terms of a arithmetic sequence is 72. What is the fifth term? Okay, so sometimes you have a problem like this. You feel like you don't have all the information to solve for it, because in order to get to the term, you need the initial term a and the number of terms, right? You only have number of terms, and you have limited information on this. But as you set out and solve for it, it just so happen this simplifies to the nth term for you. Okay, so sometimes you feel like you don't have information. There's some hidden information in the problem over here, right? So that's why it says keep your eyes on the ball. Ask for something more complicated than the value of a specific value. Just write it out, and it actually may solve itself for you. So this one is a finite arithmetic sequence. You have these, and you're trying to solve for k, which gives you a 13. Doing these exercises really helps you understand it. So because I don't want to spend more time, so I'm gonna just go over to the definition of geometric sequence. I do want to introduce that. Like I said, this is like a very light touch on the whole, a very deep subject that eventually get you to all the college math. So I'm not gonna go. There's all these rabbit holes I can go down to, which I don't want to at this point. So I'm just gonna quickly go through it. So geometric sequences. The only difference between arithmetic sequences and geometric differences is how they relate to each other. So arithmetic is the common step forward. A geometric sequence are the difference. The steps are the times the ratio. Okay, so if we have a, the arithmetic, the a plus n minus 1d, an. Okay, so an minus 1 equals to d, right? So we have this. We have each step forward. For, let's see, maybe I'll just call it bn of a geometric sequence is a multiplied by r n minus 1. Okay, the difference is bn divided by bn minus 1 equals to r. The ratio of the two consecutive terms is constant. The difference, so the here is the difference, so we take a subtraction, and here we do a ratio or quotient with dividing the two numbers. This is the only difference in terms of how we define it. Okay, again, the sequence is more general. When we talk about geometric sequences, we're saying the next term is r times the previous term, right? The other way to do it is to say bn equals to bn minus 1 times r, right? Okay, so that's the only difference. However, that small difference brings big consequences. Okay, so find the formula for the nth term of the sequence. 1.25, 2.5, 5, 10, and 20. Sometimes it's really hard to see, but this one you can say the first term is 1.25. This next number doubles the previous one. This number doubles previous one. This number doubles previous one. So this multiplied by 2 to the n minus 1's power. Okay, so the fact that you can see it all based on the familiarity of the concept from before. Okay, so if you are really used to doing all the exponents and stuff before, like learn it already, practiced enough, and you'll be able to spot the difference. Okay, a geometric sequence with the first term A and common ratio R has the nth term of A, R, and minus 1. Okay, so that's just the definition. Okay, so let's see the next one. We have 3x, 12, x, y, z, and 27. Okay, so we know this is 3 to the first power. Don't know this, don't know this, don't know this. This is 3 to the fifth power. Or if this is A1, A, this should be A multiplied by R to the fourth power n minus 1. Okay. Actually, this is not this. This is 3 to the third power. Okay. All right. So, and this is 3 multiplied by 3 squared. Okay. So we have A equals to 3. A equals to 3. So that means this is 3 multiplied by R fourth equals to 3 multiplied by 3 squared. 3 cancels out. R fourth equals to 3 squared. R equals to square root of 3, or 3 to the 1/2 power. Okay. So then x will be 3 multiplied by square root of 3. Y equals to 3 multiplied by square root of 3 squared, which is 9. And z would equals to 3 multiplied by square root of 3 to the third power, which is 3 squared, actually 9 square root of 3. Okay, the distance or the increments are negative, that are square root of 3. You multiply it to the previous term. So here's our sequence for the geometric sequence. Make sense? Okay. We call the square root of a product of two numbers our geometric mean. You know, if you do the square root, that's geometric mean. And we calculate the normal averages as the arithmetic mean. That's the definition also we introduced in the first year. And now you learn the source of those terminologies. Okay, if a term of a geometric sequence of positive numbers is exactly in between two other sequences, and the term is the geometric mean. So this is what we, similar to what we learned, is if x is y is in between, directly in between x and z, then y equals the average of x and z. If it's in the geometric sequence, and then y equals the square root of x multiplied by z. This is that definition. Okay, now by rushing through, I finally get some time, 15 minutes for my 24.1 geometric series. Metric series. Okay, so this becomes very interesting. Okay, we have a lot more that we can cover, so I'll just do my best to try to figure this out. Like I mentioned before, when it comes to how to go from series to, sequence to series, it's the same. It's just add up the first n terms. Okay, but however, we'll end up with a different formula. We'll see. Right. Let's just go there. Okay, so find the sum of a geometric sequence with the first term A, common ratio n, and n terms, right? Wow. Okay, so the first term A equals to 1. Okay, A n equals to 2048 in this case. All right, let's go back. How did we end up? Okay, so this is the S equals to sum of this. So the first term A, then, okay. Okay, so the A2 equals to 2 equals to 1 multiplied by 2. Therefore, we know R equals to 2. Okay, so this is a serial where everything doubles from the previous one. Okay. And this equals to 2 to the to figure out what the number, the n is. Let's see. Does not tell me. So it's 1, 2, 3, 4. Let's see. How many terms? Multiply by this. Oh, I guess it doesn't tell me to solve for n. So I guess what we're doing here is to find it in terms of r and okay, so that's why. So we have this, right? So we have s equals to the sum of 1 plus 2 plus 4 plus 8 all the way to 2048. Okay, so remember the trick we did with the arithmetic? We add the same s, but what we end up with is we rearrange it so all the terms become the same. So when it comes to geometry, I can't just say, oh, I add another one, and it doesn't really help me. It doesn't solve the problem. However, what I can do is I can multiply everything by r. Okay, so this is just like clever tricks. So in this case, 2, right? So now this becomes 2 plus 4 plus 8 plus all the way to 2048, and then plus the last term. So the first term becomes the second term becomes the fourth term. So I'm just lining it up. This is 4096. Okay, so we have an extra one over here and extra this over here, right? So now I have this lined up. So now instead of adding the two, what I'm gonna do is rs subtract s. So all the middle terms are gonna be canceled out. Okay, in this case, it will be 4096 minus 1. This will be a rn minus a. Okay, so this is the first term a. This is the first term multiplied by r to the n minus 1 term. It's a geometric series, and that equals to s, factor out the s. So we have r minus 1 s. Now, as long as r is not 1, which, by the way, if it's a geometric series, it's a trivial series. If r equals to 1, it's just like everything will be, each term will be a, right? And then that will reduce to a arithmetic series or sequence. So we typically define that r is not 1. When r is 1, this geometric series geometric sequence degenerates into a arithmetic series sequence. So now we have this, right? So the s therefore is, if I divide both sides, a over r minus 1 multiplied by r and minus 1 minus 1. Okay, so this is what we wanna get to, is the a formula for the geometric series. Okay. Okay. So the way to describe is this is the difference between the last term and first term. Last, subtract the first and divide it by the ratio minus 1. Yeah. Okay. So that's the series, the definition for series equals to a r m minus 1 r minus 1. Look, this note this is very different from a what was the other one? A n, sorry, a n plus d, sorry, n minus 1 divided by 2d, right? That was the one I was writing out earlier. I should have this remembered. I'm just yeah, I'm missing an n. It doesn't look completely right. Okay, now it's right. So this is geometric. This is a Riemann series. This is how they are defined. Okay, so if anything, remember, you don't need to remember everything else. You remember what is a Riemann series? It's an equal step forward. And what is a geometric sequence? It's a equal magnitude or power forward, and then the series are just adding up the first n terms. Let's see if we can do some exercise to make that clear. So we have this. Okay, this actually is how we used to early on to come up with some nice tricks and nice quick way to solve for complicated problems. Okay. Your field factorization we studied. Okay, so those are side notes. I'm not gonna cover that. Okay. Evaluate. So I'm just gonna talk through it. I only have 6 minutes left. I'm not gonna write anything down. So evaluate the infinite geometric series. So for this time, it's like dividing two, or the ratio. These numbers never end, and the ratio is 1/2. Okay, we're halving it. So the first one is 1/2. The next one is half of that. So this is the series, by the way. When we look at the geometric sequence, I mean arithmetic sequence, I can go back up, line them up as a line on the numbers, right? When we're talking about, so this one comes after that. We're talking about geometric series. It doesn't have as nicely of as nice of a format. So this is the series. Okay, so let's see if I can make it clear. Difference between the series and the sequence. Okay, so a arithmetic sequence, you can line it up and they all have the same distance, right? A arithmetic sequence, basically adding up all these. I can't draw it. I don't think there's an easy way to graphically represent it. You're adding it. You're basically increasing it. The more you add becomes bigger. In this case, you are you can line these up. You can line these numbers up. It's kind of a spiral. It goes down smaller. But when you add them up, you add the first term, the next term is half the length, which increases 1/2 to 3/4, and then you add another one, you add another small piece. Okay, so this basically becomes, if you add it, eventually you see you're going to be approaching 1. Okay, if it goes on infinitely, it will equals to 1. The sum will be equal to 1. This actually applies to 1/3, I think. Might be wrong. Might be a factor of some sort. It's the same shape. Okay, so yeah, so if we're adding, we come across things like this before. So we're adding it, we're doing this, and we end up with this. Yeah, so yeah, I was right. So it doesn't matter if they start with 2 or 3, eventually this term drops out and it becomes really, really close to 1. All of the fractions, if you add it up, the sum will be 1. Okay, if it's an infinite number of series, because you can add infinite more to it. The details we'll learn here are the beginning steps of calculus. You'll learn more in a few years when we learn the concept of limits. So that's why I don't want to get too much into it. Okay, so if we were to add this is start with 3 and it's dividing out by 1. This is like starting out at 1, incremental by 1.1, right? So this is what we call a degenerating series. The number as you go out becomes really, really small. So therefore you can figure out the value of this by, looking at this. It give you this, and there will be 2, 3 and 3, sorry, 9 divided by 2. Okay, this one is what we call a expanding theory, 发散. It becomes bigger and bigger. So if we add it up, it's gonna it's going out of scope. So we cannot evaluate this. This becomes smaller and smaller. Okay, so it will explain. Yeah, it's divergent, right? That's the word. This series become a bigger and bigger. It's a divergent. It diverges, so we don't have a number, and this becomes smaller, smaller, and it converges. Okay, so only when it converges and converges to a single point, you can find it. It folds on itself and becomes smaller and smaller. But this one it expands on itself, become bigger and bigger. So half of the time we can solve it, and then half the time we can't. So sometimes when you get to that point, you have to figure out whether it's diverging or convergent. It's not always easy, but that becomes an important part. Okay, so over here I have 1 minute. Find the formula for the sum of infinite geometric series for the first term A and ratio. This just generalize it. When R is less than 1, it doesn't matter where we start. Okay, the starting point really doesn't matter. So the first one we start with 1/2, this one we start with 3. As long as R is less than 1, even, it doesn't matter what's positive or negative, it converges. Okay, if this one is greater than 1, it diverges. That becomes sort of what I was saying, half of the time, half of the time. This is what you can, you can, what you call it? You can decide whether there is a solution or not. We said R equals to 1, it degenerates into A's, and series of A's, it becomes an arithmetic series. And when it's R equals to -1, okay, so R equals to 1, it degenerates into a arithmetic sequence with a step of 0. So it's not going up, each one is the same. It becomes a very simple singular case. When this is a -1, it becomes oscillating, right? So the sum, there are 2 cases of, like, you have the first one, you have 8, and then you have 0, and then you have 8.